plan is to talk for certainly no more than 45 minutes, hopefully a bit less than that, and otherwise allow plenty of time for questions and, you know, have a discussion session at the end. And I am also able, Richard and Chris, if it would be useful, to make my slides available as a PDF copy that you can put on your secure website if you have such a thing. So deep geological disposal of radioactive waste. It's a technically really challenging project. It involves engineering and material science, and clearly a lot of geoscience and geology and geophysics and so forth. So why have I started with a slide with a lot of happy, smiling faces? Well, I think that maybe the most important point that I want to make is, despite all the technical challenges, I think everyone that's involved in this project, either within my company, RWM, or across the supply chain, or the various political and regulatory stakeholders that we have, accepts that despite the great technical challenges, the greatest challenge of all is what I call the people challenge. It's a consent-based process. No community is going to be tapped on the shoulder and told it's going to be you. It's a consent-based process, and it involves RWM working with communities, building trust, making certain that everyone who's involved in the project understands you know, exactly what the technical mission is about. So the names in white there are some of my colleagues, and these are stills taken from videos that we made a couple of years ago to support what we call the National Geological Screening, which I'll talk about a little bit later. But the two photos there with yellow captions, I think, are particularly interesting. So you might have heard that just this week, Sweden announced that the Östhammar municipality have voted in favour of hosting a geological disposal facility at Forsmark within their municipality. And what you see there on the right is the former president of SKB, which is the Swedish equivalent of my company, RWM, with the mayors of the local municipalities, happy, smiling faces. They've worked with SKB over a period of about 20 years, and you know, they fully understand the implications of the project, how the waste material is disposed of, the implications in terms of long-term investment in jobs and infrastructure. And then the second photo with a yellow caption down in the bottom right there is from Carlsbad in New Mexico in the United States, which is the location of the world's only presently operating deep geological disposal facility. It's hosted in a thick Permian salt body. And I'm pictured there with one of my colleagues, Sam King, on the left in the front row, with a number of stalwarts from the local the community in Carlsbad. The mayor is there, the district judge, the county commissioner, a number of people who have provided really long-term support for the project. So the point that I would emphasize is really this project is all about working with communities and making certain that everyone understands the technical mission of the project. Right, so let's go on to the first slide. Oops. Ah, there we go. Richard, a little sort of box has popped up in the bottom there. I think it might have been hide thumbnail. Okay, that's fine. A little bit about me. Thanks for that introduction, Richard. I've worked in the university sector. I've worked for big PLCs, particularly BG Group and Shell. So in BG Group, I worked with Richard. I'd worked with Shell right at the start of my career. So when Shell swallowed up BG about 4 years ago, I thought it's time to do something new and fresh and interesting, and radioactive waste disposal is certainly all three of those things. I'm going to talk today, this is a fairly general talk with the emphasis on geoscience, but a number of introductory points that I want to make just to give the project some context. And I am right at the end of the talk just going to say a few words about the specifics of Cumbria and the local geology of Cumbria here, if for no other reason than just to stimulate discussion after I finish speaking. So then I should say that a lot of the slides have got a lot of information on them. In the interest of time, I'm not looking to cover all of the information, but what I'm going to do is just pick out some of the key points. Deep geological disposal of radioactive waste is UK's largest environmental project. We, RWM, are part of the Nuclear Decommissioning Authority, but actually I consider myself not to be part of the nuclear industry. I think really that we're part of the environmental industry. So what are the three essential ingredients in order to find a location in which we can dispose of Britain's radioactive waste legacy? Well, they're there in green, in mauve, and in that sort of browny colour at the bottom there. I've emphasised the first point, a willing community, a suitable site, both in terms of the geology and whether the geology is suitable for the design engineering and also suitable for the safety case. In other words, are we able to demonstrate to regulators, particularly the Environment Agency and the Office for Nuclear Regulation, that the site that we've chosen has sufficient integrity in order to be suitable for permanent disposal of the radioactive waste material. And then thirdly, a point I'm not going to dwell on in this talk, but very important, is we need suitably packaged waste. The third bullet point down there talks about containment, isolation, and passive safety. And really, I think of these as being the bywords for deep geological disposal. So in common with almost every other country that faces the challenge of how to dispose of its radioactive waste legacy, and I say almost every other country because Scotland has a separate policy, but England and Wales have opted for deep geological disposal. And this is all about containing the radionuclides such that they can't migrate into up to the surface where they could harm people and the environment and get into the biosphere. And it's about isolating the waste. Isolating it from what? Well, from two things really. One is surface processes, which for Britain particularly means earthquakes and glaciations, but also isolating it from what we call inadvertent human intrusion, which is a bit jargonistic. In other words, future generations or maybe even future civilizations mining into the facility. So it needs to be deep in order to keep it away from surface processes and away from any interference from future generations. So when I say deep, it will be at least 200 meters deep. When you look at other geological disposal facilities around the world, they're normally around 500, 600 meters depth. And then the last point there just emphasizes that this is about disposal, not storage. So presently, UK waste is stored at about 25 sites around the UK. They're shown here. About 70% of the inventory is on the West Cumbrian coast at Sellafield, and then most of the other sites shown here are currently working or recently decommissioned reactors where spent fuel is being stored at the surface. The sort of animation cartoon really here just gives you a flavour of what a geological disposal facility could look like. So you can just see it's fairly small. The surface facilities here up to 2 square kilometres, probably about the same sort of area and order of complexity as the Channel Tunnel entrance down around Folkestone. And then the subsurface consists of a network of tunnels and vaults and galleries, with the higher activity heat generating waste occupying the larger space here. Needs to be more widely spaced in order for the heat to wick away. And then the intermediate level waste, i.e. non-heat generating, occupying a smaller space on the left-hand part of this diagram. Doesn't generate heat, therefore it can be more closely spaced. And you can just about see here that the subsurface is accessed, in this case, by I think 3 shafts are shown there, and also a ramp or a drift that a train could go down, or a number of trucks, or maybe robotic trucks or something like that. I think the really important point about this diagram is I wouldn't like to give the impression that we know what it's going to look like, because that is entirely dependent on which community comes forward, what geology they have. And to give you an example of the sort of variety of options that we're currently working with, okay, the surface facilities will be onshore, but the subsurface GDF itself may actually be off the coast, maybe as much as 20 kilometers off the coast, much the same way as you may know of the Bulby mine in the northeast of England, where you've got surface facilities on the coast, and the mine, which is mining polyhalite and potash fertilizers, extends as far as 13 kilometers out under the North Sea. So a huge range of different options that we can talk about later if people are interested. everything really dependent on the nature of the real estate that we have to work with, depending on which communities come forward. So I showed you in that cartoon on the last slide, you could just about see the surface facilities, and these are just artist's impression. Again, just giving you a feel for what the surface facilities might look like. So here they are in a sort of inshore interior setting, and here they are on the coast here. Both of these artist's impressions are showing the material brought in by railway, which is almost certainly going to be the case. I suppose in this coastal setting, much the same way as Sweden has done, the material could be brought in to a bespoke port that could handle the waste. It could be processed at the surface facilities here before it goes underground. Huge range of options, again, depending on what communities we work with. So really what I want to do here is just say a few words about the nature of the inventory. So deep geological disposal is all about disposing of what we call higher activity waste. In other words, waste that is too harmful to be disposed of in the low-level waste repository just a few kilometers southeast of Sellafield at Drigg. And it looks like a fairly fussy graph down in the bottom right of the slide there, but actually it makes a simple point. And the point that I want to make is that activity, in other words, the strength of radioactivity is shown by the green bars, whilst the volume of the waste is shown by those sort of grey, mauvey, purple bars. And the point that I'd make is that the volume of heat generating high-level waste is really very small compared to the huge volume, or the relatively large volume of non-heat generating intermediate level waste. So this inverse relationship between activity levels and volume. And I should say that by contrast to, for example, you might have read a lot about Sweden and Finland. Sweden, for example, has about 2 different waste streams, both of them consisting of spent fuel from their presently operating reactors. As many of you will know, Britain has been in the nuclear game really since the invention of nuclear technology right at the end of the Second World War. And this is a picture here of Sellafield, a sort of particularly foreboding photo that I chose there of Sellafield. And what you can see in the picture there is Calder Hall, no longer working, but the first reactor in the world to produce electricity for the national grid. It also produced plutonium for the weapons programs. The 2 stacks here, I think both of which are now demolished. Those were essentially plutonium producing reactors. And then in the foreground, this big sphere here is one of the world's earliest advanced gas reactors. Really, Sellafield is a giant experimental laboratory, and it's difficult to imagine now, but in the white heat of technology, you know, particularly after the Second World War, but extending into the 1950s, when there was a real rush to develop nuclear technology, both for power and also for weapons technology, very little thought was given at that time to the sort of disposal fate of the waste that was produced from Sellafield. And I don't think you'll find anyone from the chief executive of the Nuclear Decommissioning Authority downward who would argue that, you know, we basically need to get Sellafield underground and disposed of and safe as soon as possible. In terms of the way it's managed in a really, you know, to really world-class standards, but it's an environment, and there are hazards there which are widely acknowledged to be hazards that we can't tolerate, you know, for decades or for hundreds of years. So really a large part of deep geological disposal of radioactive waste is about putting Sellafield underground and out of harm's way. I spoke about intermediate level waste, non-heat generating versus high level waste, heat generating waste. And what is shown here in these cartoons are 2 different disposal concepts. On the right for heat generating waste, and on the left for non-heat generating intermediate level waste. And again, I make the same point that I made before. None of this is set in stone, if that's not a dreadful pun. It really depends on the nature of the geology, the chemistry of the groundwater, the structures and the stresses in the crust at those hundreds of meters depth. But just to give you a flavor for how we might actually package and dispose of heat generating waste. The cartoon here shows that the heat generating waste put in copper canisters, much the same way as they do in Sweden, or they will do in Sweden and Finland, 5 centimeter thick copper canisters with a very clever method for welding the lid onto those canisters, so hermetically sealed. And then the canisters themselves, let me just get my pointer up, the canisters themselves sort of entombed in a buffer comprising bentonite clay. And the idea of the clay is that when the facility resaturates, it swells and prevents any groundwater getting to the canisters. So that's the high level or heat generating waste. What about the intermediate level waste? And you remember I made the point that we've got a much greater volume of intermediate level waste than we have heat generating waste. Well, the big challenge with intermediate level waste is because it contains organics and because of processes like radiolysis and corrosion, it generates gas. And therefore, unlike the copper canisters I described here, the waste can't be hermetically sealed. It's placed in stainless steel canisters, they'll probably be stainless steel, with filters on them, special filters called HEPA filters. And what that means is that over a period of just a few hundreds of years, some of the waste will escape into the near field environment. So this pale gray color here shows depicts a highly specialized cementitious grout that I'll talk a little bit more about in a minute, that really prevents the radionuclides from migrating far away from the canisters in which they were originally emplaced. So there's a heck of a lot in this diagram here, but it really just expands on the points that I made there about intermediate level waste. And as we go from left to right here, we're increasing in scale from the scale of an individual canister here to the scale of that sort of half a kilometer, maybe a kilometer depth down into the crust, but we're also increasing in time scale from a few hundreds of years to a million years on the right hand side here. So I should say that the time scale over which the regulators will require RWM to demonstrate the integrity of the whole barrier system is up to 1 million years. And of course, you know, we're all geologists and geoscientists in the audience here. People understand that over a period of 1 million years, a lot of things which we can't quite appreciate on a historical human timescale are a near certainty. So for example, particularly germane to the UK environment is glaciations. Anyway, let me just work from left to right. So at the scale of the individual canister, I mentioned that they are designed to leak because they can't be hermetically sealed, because they generate gas. Radionuclides will leak into the immediate near field environment, which is shown with this sort of browny color here. So that browny color is a hyperalkaline, sort of very specialized, very highly porous, cementitious grout. The idea of the high alkalinity, the high pH, is that radionuclides have very low solubility in alkaline environments. And the idea of the high porosity is that that maximizes the way in which radionuclides will be sorbed onto the surfaces of the pores within this cementitious grout. Then jumping up a scale again, so here you can see a number of canisters within the grout, and then here we're looking at the near field geological environment. So what is it that we require the rock to do? Well, I'm going to talk a little bit later about different sorts of rocks that could satisfy the requirements for a geological disposal facility. But the really key thing is that those rocks must contain either no groundwater, for example, evaporites, or very little groundwater, for example, Jurassic or Cretaceous clays, or if they contain groundwater like you would get in highly fractured rocks like granites, or in your neck of the woods, the Borrowdale volcanics, we need to be able to demonstrate that that groundwater moves only extremely slowly and is isolated from the surface environment. Because, and this is the last of these little circles that I'll talk about, what we need to be able to demonstrate is that it will take a very, very long time for any radionuclides to migrate near to the surface where they could contaminate the biosphere. And by a very long time, I've spoken about hundreds of thousands up to 1 million years. it's very difficult to model processes beyond 1 million years, but also the point about 100,000 years is that the average level of activity of the radioactive waste by 100,000 years will have decayed back to background levels. And by background levels, I mean the levels of activity that you find in natural uranium ores. So has this been done before? It's what we call a first of a kind project. Clearly the UK doesn't have a geological disposal facility, so in that respect it hasn't been done in the UK before. I mentioned that there's a working facility in the United States, and Finland, Sweden, France, Switzerland are ahead of the UK in terms of developing their facilities. But what I want to talk about in this slide is about natural analogues, because you can argue really quite effectively that nature has done this before. And if I start on the cartoon on the left-hand side here, you might have heard of the Cigar Lake mine in Arctic Canada in Saskatchewan, which is a really high-grade, it says it there, doesn't it, 20% uranium ore that's been mined for about the last 30 years. The ore is sitting in a very low permeability, organic-rich mudstone, much the same as the kind of mudstone in which we might develop a geological disposal facility in the UK. And the important thing is that there's no evidence of radionuclides either in the overburden or at the present surface. So in other words, this 1.3 billion year old uranium deposit has been contained by this low permeability mudstone over an extremely long time period. A few other analogues I want to talk about. This clearly is not a natural analogue, but it makes a very simple point. It's a 400-year-old cannon barrel. This nicely preserved end of the cannon barrel was sitting in an anoxic, i.e. oxygen depleted mud, and you can see it's really quite well preserved, whereas the other end of the cannon was sticking out into the oxygen-rich seawater. So it makes the point here that what we're looking for is an environment which is depleted in oxygen. And one of the ideas of geological disposal facilities is that when the facility resaturates in a natural way with natural groundwater, the oxygen within that groundwater will be used up relatively quickly by processes like corrosion, for example. And thereafter, it would be an anoxic, i.e. low oxygen environment, which then minimizes the amount of corrosion of the canisters that can go on. And then the last analogue I want to talk about, which again is a natural analogue, this is an example from Jordan, a place where a hyperalkaline, completely natural hyperalkaline volcanic plume flooded through these red mudstone rocks you can see here, flooded through fractures in the rocks. And the interaction between the hyperalkaline plume and the natural chemistry of the rock caused clay minerals to be precipitated within the fractures, in a very similar process to what we envisage would happen with groundwaters that have gone through that hyperalkaline grout within a geological disposal facility that I mentioned a little bit earlier. So there are many analogues that we can take from nature and from archaeology and from history that are quite an effective way of telling this story. So what I want to do in the remaining slides is just to talk about some of the sort of key features of the geology that we can use to demonstrate or to develop integrity and long-term safety for a geological disposal facility. And so the first of those, unsurprisingly, is rock type. So we're a little postage stamp piece of continental crust, certainly compared to the USA and other countries, but as you will be aware, we have a hugely rich diversity of different rock types and different geological ages. And for the purposes of defining different types of rocks in which a geological disposal facility could be constructed, we recognize three broad categories in common with the way that other countries have approached this challenge. The first of those categories, well, all three categories are defined according to the way in which groundwater behaves or how much groundwater they contain. So let me tell you what I mean by that. So the first of these categories is salt, so natural rock salt, halite or maybe some potash salts. And the point about halite is that it contains almost no groundwater. If it did contain groundwater, then you wouldn't have 250 million year old Permian salt preserved in the subsurface because it would have been dissolved away. So salt works really well because very little or no groundwater. Second category, which I've just briefly mentioned already, is Jurassic and Cretaceous clays, like the Oxford clay, the Kimmeridge clay, the Gault clay that you get down in the southern part of Britain. And the point about these is that, yes, they do contain groundwater, but it's within micropores and even nanopores, and it moves so slowly through these rocks because they have such low permeability that the process that dominates movement of colloids and indeed radionuclides through these rocks isn't pressure-driven flow, but it's diffusion-driven flow. In other words, contaminants, be they colloids or radionuclides or anything within the groundwater, moves by concentration gradients rather than by pressure-driven flow. And then the third category is what we call higher strength rocks. And this is a real bucket term for a whole variety of different sorts of rocks. The common feature that they share being that water moves through them via networks of fractures. So this might be a granite. In Cumbria, it might be the Borrowdale volcanics. It might be a highly compacted sedimentary rock. So the examples I'm showing here these are slates in Llanberis Pass in Gwynedd in northwest Wales. Actually, Dinorwig is where Electric Mountain is, if you've ever been to the pump storage station there. Oxford clay here from Cambridgeshire. And then I mentioned briefly Bulby Mine, the evaporite mine in the northeast of England, you can see here. So rock type is going to be really important. Secondly, geological structure. And I make the bold statement up there that structurally uncomplicated is better. It's a funny thing that all the things that excite all of us as geologists is exactly what we're not looking for. What we really want is flat-lying, layer cake, really boring geology. What we probably don't want is the kind of thing that you see. This is an example from Cornwall, from just south of Bude. These are middle Carboniferous rocks, spectacularly folded. So structurally uncomplicated is better. So the map here shows the Mendips, south of Bristol, southwest of Bath. And what do we have in the Mendips? Well, the caption gives it away, really. We've got fractured limestone, we've got big thrust faults. You can see big folds here. The Carboniferous limestone is shown in the various blue colors. The limestone itself is full of caves and fracture systems. And of course, at Bath, you have 45 degrees centigrade spring water bubbling out at the surface. In other words, evidence that there's a fast pathway connecting the relatively deep crust to the surface. So not ideal on the scale of the map here, but, and it's a really important point, bear in mind that the area of a GDF, of a geological disposal facility, if we were to dispose of all the inventory in one facility, is no more than 20 square kilometers. So we're only looking for a fairly small patch of real estate, even though on the regional scale, structural complexity here is not on the surface of things particularly attractive. So the third sort of geological feature that I want to talk about, or geological heading, if you like, is what we call natural processes. And particularly of relevance here is glaciations and earthquakes. I'll deal first with earthquakes. The map here shows the epicenters. It's just downloaded directly from the British Geological Survey. The epicenters of earthquakes across the UK over, I think, probably about a 50-year period. So the magnitude 6 earthquake, which is the biggest event, certainly of my parents' lifetime, offshore southern North Sea and Dogger Bank here. The point I make is that, okay, Britain is tectonically fairly quiet. That doesn't mean that we don't have earthquakes here at all. We certainly do. Many of us may have actually experienced small earthquakes. I have, living down here in Birmingham. But the important point is that there's nowhere in Britain that would cause, there's no particular site in Britain that would cause us to downgrade a site at this very early stage of looking for a possible location for a geological disposal facility. Once we're working with a community and we're beginning to focus in on specific locations, then we would need to do an enormous amount of work to demonstrate the pattern of seismicity of earthquakes over an historical time period, and to demonstrate that any facility that we were constructing would be what we call seismic qualified. But earthquakes happen. They're not particularly big compared to some other countries. So the second natural process I mentioned that's of particular relevance to the UK is glaciations. And the map here, and I apologize for the fact that it's rather low resolution, but it shows thickness of permafrost or frozen ground modeled across the UK. And if you can see the legend down here, in parts of the UK, we would predict up to 500, 560 meters depth of frozen ground. So the important point here, without going into too much detail, is glaciations have a profound effect on the sort of hundreds of meters depth in the Earth's crust. Permafrost, the weight of an overlying ice sheet, the introduction of large volumes of oxygen-rich groundwater. So again, we need to understand the impact of glaciations over that tens and hundreds of thousands of years period after a geological disposal facility was decommissioned. The penultimate, so I've got 5 of these geological headings that I want to talk about. This is the second to last one, and just talking about groundwater. And I think I've made my point in an earlier slide already. We will need to select a location either where groundwater is absent, or where deep groundwater systems are isolated from shallow groundwater systems, and that we can demonstrate it moves only very slowly. So one of the things that you get if you visit the Swedish or indeed the Finnish facilities, they give you a little bottle of groundwater. I've got one in the other room from where I'm speaking to you here that has on it 50,000-year-old. In other words, the point they make is that they've used stable isotope analysis to demonstrate that the groundwater in the area where they're constructing their facilities has been resident or stagnant for tens of thousands of years. And a similar point here is made from this example from the Triassic of the East Midlands, down to the south of where you are, showing that at only 400 meters depth, you've got 100,000-year-old groundwater. In other words, groundwater that has sat there not moving for 100,000 years. A really powerful piece of evidence in terms of demonstrating to people this point about the fact that groundwater needs to be absent or moving only very slowly. And then the last of the sort of geological points that I want to make is about resources. What I mean by this is natural resources, coal, oil and gas, metalliferous resources. So the map in the top left here shows the main gas and oil shales of the UK. We've got the Liassic of the Wessex Basin, the Lower Jurassic of the Wessex Basin, Kimmeridge Clay or Upper Jurassic of the Weald Basin. Of course, best known is the Carboniferous Nemurian shale that Quadrilla undertook some fracking experiments on in the Blackpool area, and then the Carboniferous oil shales of the Midland Valley. So everyone knows that natural resources have been exploited in the UK for, well, I was going to say 200 years, but actually much, much longer than that. And the point I would make is a simple point, and that is that we would look to avoid constructing a GDF in a location that has been intensively exploited for natural resources. The reason being that whether it's coal mines or metal mines or oil and gas fields and development facility, production facilities, comprise a whole network of boreholes and shafts and tunnels and so on that disturb the groundwater pattern. And of course, what we're looking for is relatively undisturbed geology, and certainly geology in which there are no fast pathways from depth to the surface. Okay, well, I said before, has this been done before? And I talked about natural analogues. And one of the questions that I and we very often get asked is, are other countries doing this? And, you know, I've mentioned a few countries already. So Sweden, Finland, France, Switzerland, Japan made a very exciting announcement last week that the first community in their siting process has, volunteered to enter their siting process. So there are a number of other countries that are facing the same challenge as to how to dispose permanently of their waste legacy. And the examples you see here: deep borehole drilling in the Alpine 4 Deep of northern Switzerland. That's ongoing as we speak. They've narrowed down to 4 potential sites, all of which are underlain by a Colovian Oxfordian sort of extremely low permeability claystone. Here you see vibro-sized trucks that acquired really nice high quality 3D seismic data, on the basis of which they're now drilling these deep boreholes in Switzerland. SKB, I talked about SKB and the Swedish project right at the start of this talk. They're constructing their facility. They've just got the go-ahead, they've just got a positive vote from the Östhammar municipality just this week, and they plan to construct their facility, unsurprisingly, in Archean granitoid high-strength rocks. And then lastly, the French disposal delivery company, Andra, their favoured site is at Bura in the southeast part of the Paris Basin. It's in a very similar Colovian Oxfordian low permeability claystone to what the Swiss are planning to construct their facility. And then here you can see some concrete lined tunnels about 450 meters underground at Bura. So that's almost it from me. And I just wanted to maybe stimulate some of the discussion that hopefully we can have afterward, and just say a few words about Cumbria. So some of you may know that both Copeland Borough Council and Allerdale Borough Council have been public about the fact that they are in discussions with Radioactive Waste Management. I read about it in the Whitehaven News, but I know it's been fairly widely publicised, and that they plan to form a formalised working group with us in the not too distant future. They have been very clear, and again, this has been widely publicised in the press. I read about it on the Cumbria Trust website, that right from the outset of those discussions, they are effectively ruling out the idea that a geological disposal facility would be within the boundaries of the national park. And therefore, what that means is that the likelihood is that we would concentrate either around the coastal fringe here. I love this old geological map that I picked out here, or in the offshore region in the Irish Sea. And the point that I've made in the caption here is a simple one worth remembering. Much of the western part of the UK, much of the western coast of the UK, is defined by a network of faults that are a carryover from an ancient Triassic rift system. And what that means is that the onshore parts of the western UK consist of uplifted, deeply eroded old rocks, such as you find in the Lake District. And as soon as you jump to the offshores, you see in this old Nirex cross-section here, you see completely different geology. So you'll be aware that as soon as you jump into the Irish Sea region, you're into Triassic Mercia mudstone and Triassic Sherwood sandstone. And indeed, not far off to the west of this map here, you've got the Morecambe Bay gas field, which is producing from the Sherwood Sandstone Reservoir within the Triassic. So very different onshore and offshore geology. And given that the national park has been ruled out from the process right from the outset of our discussions with Copeland and Allerdale, I think that it's going to be really interesting to see how those discussions go forward and to see the potential of the offshore region. And I think with that, I just want to again thank you for attending, and thank you for your attention tonight, and just draw your attention to our website. There's a wealth of information on there, and I would say watch this space. I hope that there's going to be a lot more activity and announcements in the media in the near future. So Chris and Richard, thanks very much, and I'm happy to take any questions. Thank you.
Well, thank you very much, Jonathan, for that stimulating talk. I'm sure our audience has been given plenty to think about, and I'm sure there's going to be a lot of questions for you to answer. So if people would like, anyone who has a question, if they would like to just click on that raise hands. I'll know who you are, and then you can unmute and put your questions to Jonathan. So I'll wait and see what happens.
I think you've had a written question already.
A written question.
Yeah, in the chat.
I can't see anything, Chris. I mean, I can. So if you read out the written question to me.
Okay, there's a question from Tony Grindrod. Jonathan, as China expands its nuclear facilities, what disposal sites are they looking at?
I mean, I myself have had, I've been pretty lucky in the 3.5 years since I've been in RWM. I've visited almost all the major facilities around the world, but I've not been to China, but I know that they've not decided on a location for their geological disposal facility, but actually they've gone down a similar route to what happened in the UK in the 1990s, and that what they have developed is a rock characterization facility, or you might otherwise call it an underground rock laboratory. It's in northwest China, sort of on the edge of the Tibet plateau, and the idea of that is they're going to use it to demonstrate and develop a whole range of different technologies that they're going to need for their GDF, for their geological disposal facility. So if you'd asked me about almost any other country, I probably could have given you a more comprehensive answer, but at the moment, it's an underground rock laboratory that they're focusing on.
Thanks, Jonathan. I've got a question from Cherry.
I was just interested to know what sort of time scale are we looking at before we actually A, make a decision, and B, build something? Because as far as I remember, we've been talking about this for the last 30 or 40 years. Where are we in that time scale?
Yeah, 40 is not an exaggeration, Cherry.
Yeah.
So this is one of a number of projects on the government's books at the moment that goes under the category of a major infrastructure program. And, you know, major infrastructure programs have there's a whole sort of bibliography of regulations and planning permissions and development consent orders that go with that. So major infrastructure programs are a long-term initiative in any case. When you add to that what we're dealing with here, it's not the most uncontroversial of environmental projects, and I have emphasized all the way through the talk that it's not going to be imposed on any community. It's about community consent, and you know, certainly I could easily fill another talk, if not several other talks, on the history of the program, the failed process in the 1990s that quite possibly some members of the audience might know a lot more about than me. There was also another brief process between 2008 and 2013 that stalled, and here we are having a second, you know, really good attempt. I mean, I would say, not just on the basis of what I've seen, I've only been with the company 3.5 years, so I haven't lived through those other siting processes, but what I've seen and what my colleagues tell me is that RWM, my company, is in so much better a place in terms of community engagement and openness and accessibility and all those things that we need to live and breathe than we were in the past. But to directly answer your question, so we have a whole range of planning assumptions and Gantt charts that are about 5 meters long if you were to print them out, and they're all based on assumptions. But you know, the bottom line is that from now to the point at which we decommission the facility, walk away, and effectively throw away the key, the assumption is it's a 160-year program. But of course, like any major infrastructure program, you break that down into bite-sized chunks. So at the moment, all of the focus is on developing these working groups, which it looks like Copeland and Allerdale Borough Councils will be the first of. Progressing those to what we call community partnerships, which is the point at which they begin to receive investment funding. And then as we begin to focus in on real geology and real surface conditions, developing our designs such that we are ready to actually construct the facility, probably starting construction in the 2040s. But I'm sounding vague, Cherry, because the really important thing is that, you know, we can put more money into it and hurry along the way that we do things, but the whole project will only go at the speed at which the community wishes to go.
Yeah.
Because at any point along the way, they're entitled to say thanks, but no thanks. I mean, there is a process called a test of public support, which is essentially a referendum, after which they cannot veto the program. But that's, you know, probably 15 years away, we shall see. But until then, we need to go at the speed at which the community are able to take their people with them.
So have discussions started with various communities?
Oh yes, yeah. So it's a stage. The siting process is a staged process. So the first stage is what's called initial discussions. They're private. So for example, if you put a freedom of information request into us and said, who are you speaking to? You know, we're allowed by law to say, sorry, but we can't tell you. They need to be private because of the political risk. The big excitement that I've spoken about with Copeland and Allerdale is that they are ready to form a working group. And the working group is public. A working group is when it's out there in the public domain that Copeland and Allerdale are talking to RWM and forming, a working group is the best description, and beginning to define the search area. In other words, the area that within which we might look and within which we might conduct geophysical surveys, and then after that, deep borehole drilling. And then the next stage in the process, which I briefly mentioned, is community partnerships, which is the point at which the government starts feeding investment funding into those communities.
Right.
So yes, it has started, but it's a long process.
It'll see me out.
Yes, I think
you too, probably.
Yeah, as I say to people, I think by the time we are in placing the first waste in the ground, I might well be in my own personal little geological disposal facility.
Yes.
Okay, thanks, Kerry. John Wood has a question for you now, Jonathan.
Thank you, Richard. Jonathan, you mentioned thinking about safety for future generations and even future civilizations, perhaps. I wondered what thoughts being given then to how you'd ensure that future generations stroke civilizations know where these depositories are, if we're thinking that they might need to know where they are in 10, 20, 30,000 years.
Yeah.
Presumably we're not going to leave them a USB drive somewhere hanging on a tree locally.
Well, actually, there's two questions in one there, because your mention of a USB drive is not just of relevance to future civilizations, but I mean, if you think within our lifetimes, the change in technology we've experienced, you know, I mean, I show my children cassettes and floppy disks and they just laugh and say, what is that? So, you know, we need to make certain that when we're being regulated 30, 40, 60 years from now, we have the information in a format that we can actually access it. But anyway, that wasn't the main thrust of your question. The main thrust was how we're going to mark the site. And this is actually a field called semiotics, which is a new word to me since I've been in this industry. And the first thing I would say is it's not something that RWM is spending barely any time focusing on at the moment, because you know, the emphasis is on developing communities and developing our plans for site characterization and geophysics and deep boreholes and so on. But other countries who are further ahead on the curve compared to the UK have devoted some thought to this, and there is the full breadth of different opinions. So the French, and you know, I Google it and see what you get. There are some fantastic ideas. The French have thought of things like, you know, huge chunks of black concrete, or what do you call it, genetically modified trees that sprout pink leaves, or stuff like this, you know, just some bizarre, all sorts of bizarre stuff. There is another argument that says you don't mark it at all. You simply don't mark it at all, for several reasons. One is, if we are indeed talking about future civilizations, and we're talking about multiple continental glaciations, then anything you stick on the surface is unlikely to be preserved over that kind of timescale. But the other thing is, if you put the material deep enough, and you remember I really emphasize the importance of isolation of the material, isolation from not just surface processes, but also human intervention, then there should be no need to mark it because it's deep enough. Well, there's another side to that. If you put it deep enough and future civilizations are intelligent enough and capable enough to be able to remotely sense that the material is there, then they probably are able to work out what the material is and indeed whether they want to drill into it. So I'm getting into all sorts of, I haven't really given you a direct answer to the question here, but it is a very interesting question. And from time to time, I have people from, arts faculties and design centre in London, people, who don't have a sciencey or engineering background, ringing up or getting in touch saying they'd really love to do a project on semiotics. And it's absolutely fascinating. It's not something which RWM is presently focusing on, but I do encourage you to Google it and just see some of the weird and wonderful things you get. Maybe if I can just make a plug here, who would have thought that I would have enjoyed, sort of glass of wine and watching a full-length feature film on radioactive waste disposal. But the Finnish disposal company, delivery body called Possiva, about 8 years ago, commissioned a filmmaker and gave him, and it was a him, permission to go where he liked and talk to whom he liked. And he made a film called Into Eternity, and it deals with exactly the point of your question, John. It deals with the very long term and how you mark the site. It's called Into Eternity. It's on YouTube, and it's like a piece of Nordic film noir. It's really very good, very stylish, very informative, and it'll tell you a lot more than I've told you in my brief answer here.
Yeah, thank you very much. Very interesting.
Thanks, John. Have a question from Audrey Brown for you, Jonathan.
Hello, Jonathan. I think it's really intriguing that you've chosen glaciations as one of the things that you need to concentrate on, because presumably, at least in the near future, it's going to be, temperature's going to go the other way. And so we're likely to have flooding, and probably more of the coastline of the UK and elsewhere is likely to be underwater that isn't now. And so presumably that's going to affect groundwater flow considerably. So I just wondered, well, presumably you are taking all those things into account, but you didn't mention it.
No, thanks for the question. It's great when people ask questions and you think, crumbs, I meant to mention that. And it gives me the opportunity to answer it now rather than in the talk. So it's a really relevant question. So yes, you're right. I mean, I've forgotten the name of the small settlement just at the foot of Cadair Idris in northwest Wales, which is Gwynedd Council has declared they are going to abandon and leave to the sea in 2050. So it absolutely is an issue, sea level rise and flooding. But the point I would make about sea level rise and flooding is it's only an issue for what we call the operational safety case. In other words, that 160-year period that I talked to Cherry about, when the facility is actually operating and the waste is being in place. Why is that? Well, obviously a flooding event, water is a moderator, and the potential for a flooding event actually to cause criticality if it overwhelms some of the waste material is a significant hazard and one that we will need to take account of. But the regulator that is interested in that hazard isn't the Environment Agency, because it's not, once we've closed the facility, flooding or tsunami is almost irrelevant to what's happening at hundreds of meters depth down in the Earth's crust. The relevance of flooding is during the period during which the facility is operational and the waste, some of the waste material is stored at the surface waiting to go underground. And as I said, the key thing about glaciations in terms of groundwater, one of the points that I just briefly mentioned is that glaciations are often associated with an influx of highly oxygenated groundwater. And I talked about the importance of having anoxic conditions in the facility. But the likelihood is that flooding on the surface or a tsunami or something like that is barely going to be felt in groundwater at depth. Is that a satisfactory answer? Or?
Yeah, thank you.
Yeah.
Whilst you were speaking, Jonathan, somebody called Keith has informed everybody that Borth is the village I think you were referring to on the coast of Wales.
It's not. I know what it is. It's Fishbourne.
Fishpoint, yeah.
It's Fishbourne. It's north of Machynlleth. It's been in the news a lot recently because a lot of people's houses there have gone from, well, they've gone to zero value.
Yeah, I've read about that too.
Yeah, I went on my motorbike a few months ago, and it's a really bizarre place. And you know, Gwynedd Council spend a lot of money basically keeping the sea back, and they've now announced they're not going to do it after 2050.
Well, I have another written question from Tony Grindrod. Tony, if you're there, it'd be better if you use the blue hand rather than sending written chat messages. Then you can ask Jonathan your question yourself. But Tony would like to know, actually no, Tony states there's very little high resolution 3D seismic data available for the Boland Basin. How well is the Cumberland Basin imaged by 3D, 4D seismic?
Oh, not well at all, Tony. I mean, there's NIREX acquired a small 3D survey that I think was led by Dave Smythe, who then was up at Glasgow. Obviously, you can go. You might be aware of the UK Onshore Geophysical Library, which is an absolutely fabulous resource of legacy data that's out there for anyone to download. And you'll see from going to that UK Onshore Geophysical Library website that there is barely any high quality 3D or even 2D onshore data in the Cumberland Basin. Of course, there's lots in the offshore region because of the amount of mainly gas exploration that's gone on with Morecambe, the Morecambe field, and then the fields down in the southern part of the East Irish Sea Basin. The degree to which we would use 3D seismic would depend on the geology that we were trying to image. So if we had Jurassic Cretaceous layer cake clays, or indeed the Mercia mudstone, we could expect to get a lot of really good information out of a bespoke 3D seismic survey. But if, for example, we were focusing on the Borrowdale volcanics, which is looking unlikely given that the national park has been ruled out, then it wouldn't be worth bothering with a bespoke 3D seismic survey because there aren't strong impedance contrasts, the layers are dipping very steeply, it's very heterogeneous, it's just not the kind of formation, or it's not the kind of rock unit that responds well to 3D seismic imaging. So it's a case of horses for courses, but at the moment there isn't much. But I do recommend you go to the UK OGL website and see for yourself.
Cherry, have you got another question? I can see a blue hand on your picture there.
I think that's just left over from the first question I asked.
I wasn't sure. Okay, well, does anybody else have any questions for Jonathan? No, it doesn't look like it.
Yes, I have a question.
Oh, right, okay.
Jonathan, it's not a geological question at all, but are the other countries that are developing these sites and perhaps further ahead than we are they going to be willing to import other countries' problems?
No, because actually it's not well enough known that IAEA, so that's the International Atomic Energy Agency, forbids export of radioactive waste. And a lot of people say to me, no, that's rubbish because we import Japanese waste, which is true. It comes into Barrow-in-Furness. But what people don't know is that we import a small volume of heat generating high level waste from Japan. But what people don't know is that, or don't understand well enough, is that there's boats going in the other direction, exporting a larger volume of radiometrically equivalent waste from the UK back to Japan. So, and the idea of that international treaty forbidding export of radioactive waste is you could foresee, I don't know, I'll pick a country off the top of my head, Mali, Niger, Chad, a developed country tapping them on the shoulder and saying, we'll invest £10 billion in a new railway or motorway system. And by the way, could you have our little problem here? So no, it's for us to deal with our waste and the Swiss to deal with their waste, and so on and so on. And you know, some countries that are beginning to think about radioactive waste disposal have tiny inventories and very simple inventories, you know, basically consisting of spent fuel from currently operating reactors, but nonetheless, they can't export it, they can't get rid of it. It's their problem. The one caveat I would say to that, and I think this idea is about 99.9% dead, but I did receive a delegation about a couple of years ago from the South Australian government, who were just investigating the possibility of having a global facility in South Australia. You know, South Australia is very remote. It's got good, you know, crystalline, zero groundwater geology. Ironically, it's where a lot of the world's uranium comes from in any case, so you'd be returning it from whence it came. You know, I could see that in principle, rather than every country inventing the wheel themselves, in principle, pooling resources and getting together and investing in an international global resource would be fantastic. But you can see that from the perspective of the First Nation Aboriginal communities in South Australia, you know, that's not an easy challenge to overcome. And I think that idea has been given up on now. So basically the answer is no.
Yeah. Okay, thanks.
Any more questions for Jonathan?
I'm in no hurry, Richard. So, you know, if there are.
No, I can't see any more hands going up or, we've got Nick Pierpoint.
Yeah, hi. I can't find the blue icon or the blue hand. So technology's got the better of me. But first of all, Jonathan, that was a great talk and it was really clear. I really appreciate that. And I heard you talking to the Arts Geological Society on the same theme, probably about a year or so ago. And it was very much focused on, you know, how you were canvassing other canvassing communities at that stage. And I just wondered how that work had progressed and whether or not the current pandemic has put the brakes on that type of process.
Yeah, well, firstly, hi, Nick. How are you? Great to hear from you. And thanks for the question. So you might have heard me talking to Cherry about the fact that the siting process is a stage process. And the first stage in that process, they're called initial discussions with interested parties. And by definition and by necessity, those initial discussions need to be private because of the political risk entailed in sticking your head above the parapet and saying you're talking to RWM. So Copeland and Allerdale Borough Councils, they themselves went public about the fact that they've been having initial discussions with RWM and that they're on the verge of forming working groups with RWM. So unfortunately, that, you know, all I can tell you is there are a number of initial discussions going on with a number of interested parties.
Okay.
But I can't elaborate on who they are because it would be completely, you know, sort of breaking their confidentialities and so on. But, you know, I think, I mean, I've said it several times that, you know, the news from Cumbria is really, it's probably the most exciting thing to happen to RWM in 20 years. And I would say, Nick, watch this space, you know, over the coming months and sort of year or so, because I would be hopeful that we will be in a position to announce more working groups on top of Copeland and Allerdale. But yeah, things are progressing well and encouragingly. You mentioned COVID, and it is a challenge, as you can imagine, and we need to be sensitive to the fact that you know, a lot of district councils and LEPs and local authorities, you know, they have a much bigger issue to deal with right now than a 160-year radioactive waste disposal program. So, you know, we need to get that balance right between not nagging them, but also not being completely invisible.
Yeah, okay, a difficult balancing act. Thank you.
Thanks, Nick. Anybody else have any questions for Jonathan? No? I don't think there's any more questions for you at this point, Jonathan. So
Well, I should say, Richard, if anyone does have any other questions, I mean, you've got my email.
yeah.
Please do get in touch. You know, happy to have a email dialogue or telephone conversation, or even better, once we're past COVID, I might come up and actually see people face to face. That would be brilliant, wouldn't it?
Yeah, that would be good, wouldn't it? Yeah. But okay, well, I'd like to just hand over to John Wood, if I can. Are you there, John?
Yes, thank you, Richard.
Just pass over to you.
Yeah, thank you very much indeed, Jonathan. I think you found a very interesting area to work in. I think it's probably quite unusual for a geologist to be looking, especially for boring geology, and also to be working in a field where you're considering change on a geological timescale, but that timescale is into the future as much as into the past. There can't be many people who are working in that sort of field. I certainly found it a fascinating talk, and there were a number of things I'd not considered before. Certainly, I realised that the timescales of radioactive decay are pretty large, but I hadn't thought that one needed to consider as far ahead as 1 million years in the planning, which was fascinating. And so many distant aspects to it, of course, with the not just geology but engineering, and then all those human sides of actually persuading local communities. And I imagine that will, whatever, be one of the most difficult aspects, not least because of a public lack of understanding of science in so many ways, I think. Very interesting to hear about other countries that are ahead of us and what they're doing. And finally, for those of us very disappointed by the delay in the release of No Time to Die, you've given us another film we can look at during the days of lockdown. And perhaps, Richard, we could persuade the brewery to do a staging of Into Eternity, and we could have a WGS outing. So thank you very much indeed, Jonathan, for a very fascinating talk, and perhaps we can all thank you in a way that we can, even if we're listening. So thank you.
Thanks, John.